session so far. My name is Ayyappa Chintam. I'm a Principal Solutions Architect at Yugabyte. So in this session, we're going to talk about how query execution works in Yugabyte. Before jumping into the topic, let's quickly look into the different consumption options we offer with Yugabyte. As you all know, Yugabyte is a 100% open source database, which provides distributed SQL and Postgres compatibility. Apart from the open source YugabyteDB, we offer YugabyteDB Anywhere. This is an enterprise product which can be deployed in any of the customers' data centers or cloud infrastructures. It provides Yugabyte platform UI, which helps customers to deploy Yugabyte clusters easily. On top of that, it also has additional capabilities for managing day one and day two operations like monitoring or cluster scaling, etc. And finally, we have YugabyteDB Managed, which is a service provided by Yugabyte, which is a fully managed service and that helps customers to focus on business outcomes by removing infrastructure maintenance overhead. So with that, now the topic we are going to talk about today is query execution. So that is going to be common across all the three products I just mentioned about. So if we look into YugabyteDB, this is designed for cloud-native microservices kind of workloads or any kind of workloads which requires high availability and low resiliency. Mainly YugabyteDB is inspired by Google Spanner, and it provides layered approach for distributed SQL. So when I say layered approach, here we're talking about primarily the query layer of the database and the storage layer. So when we talk about query layer, we support YSQL and YSQL. YSQL is for Postgres compatible workloads and YSQL is for Cassandra compatible workloads. They both share or use the same underlying storage layer, which is provided by Yugabyte. So this storage layer is built on top of RocksDB, and it is highly customized to provide the distributed nature like sharding and load balancing and rough consensus for maintaining that multiple replications and distributed transaction manager and MVCC. So in this talk, we are primarily going to focus on YSQL and the DocDB storage, how Yugabyte is able to provide Postgres compatibility to the distributed SQL. Okay, so if we talk about YugabyteDB, how we have implemented the YSQL layer is, we have taken the query layer, which is offered by the open source Postgres, and embedded that query layer into Yugabyte, which uses Yugabyte developed storage layer. So here in the screen, we can see that In a typical Postgres, we have a Postgres query layer, and it uses the Postgres storage layer. So what we at Yugabyte did is the replaced Postgres storage layer with uh, DocDB storage layer. Sorry. So if you look into the Postgres architecture, how when a query is uh, submitted to Postgres, how it uh, executes the query. So first we have a postmaster, which takes the query from the client and it rewrites it, and it uses the planner to decide what is the optimal plan to execute it, and it uses the executors and optimizer to execute the plan. And once the plan is created, it handles or it gives the plan to the Postgres storage layer. And how Yugabyte changed that is we use the whole the postmaster, rewriter, planner, executor, optimizer layer from the Postgres query, and we replace the storage layer, which handles the actual retrieving or storing the data. Apart from uh, changing the storage layer to Yugabyte DocDB, we have also enhanced some of the components in the query layer. So to cater to the distributed nodes which are used to execute customer queries, we have enhanced planner, executor, and optimizer to consider number of nodes and where the data is distributed and other parameters when executing a query. Since we are a distributed database, so apart from data being distributed across multiple nodes, each node has a Postgres process, which is a stateless, meaning it does not have any persistent data in that. And that Postgres process is running across all the nodes. Since we have multiple nodes in the Yugabyte cluster, any node can be used for client connections. In case of any node failures, the services will not be affected since we have DocDB storage, which provides fault resiliency by using data replication, and Postgres service is across multiple Postgres services are running in each node. The services can use any node to connect and work on the data. Okay. For query execution point of view, the Yugabyte supports most of the Postgres patterns. So for scans, we support sequential, index scan, index only scan, or reverse scans. For joins, nested, merge joins, left outer, right outer, and other Postgres features like sorting, limit offset, aggregates, and window functions, and CTs, common with clause. So these are the features which are supported by Yugabyte. And since we are talking about the query execution, so So far, we have discussed about how Yugabyte takes Postgres like query and it parses and then creates execution plan. And once that execution plan is created, that execution plan is handed over to the DocDB storage layer. So now let's have a quick look and to understand how the DocDB manages the storage layer so that we will have a complete understanding of when a query is executed, how the query is passed, and then how it is handled in the storage, how it is stored in the storage layer, first of all. And when a query is executed, how the execution works in the storage layer. So I'll give you a couple of examples later to show that how the storage is working and how you can use that knowledge when you are writing the queries. So a quick overview how the DocDB uses. DocDB is primarily based on the RocksDB, and it is highly customized to support the distributed nature mentioned earlier. So the primary nature of the storage is using key value model. So here I have given a couple of examples of internal storage, how the keys are created and how they are logically stored to give you some understanding for the purpose of visualization. Yugabyte supports primary keys and also secondary indexes. The primary keys and secondary indexes, they can be on multiple columns or single column. We support two types of sharding, or sharding in sense like two types of indexing the data. So in one is hash sharding and another is range sharding. So when we say hash sharding, that means that the primary key is hashed and then use that DocDB or Yugabyte uses that hash value to store the data in a particular bucket or tablet. When you use a range sharding, instead of converting into a hash value, it uses the value itself to identify the tablet the data resides in. Okay. Now I'm going to show you a quick data example of how the data is actually stored in the database. Okay. So in this example, I want to highlight that when we are using a primary key or a secondary indexes on multiple columns, how the data is actually stored internally. This understanding will help you when you are writing a query or designing a data model so that the workloads are optimized by understanding this storage. So here, for example, I have created two tables. The data is same. Example, it is a product number, category, and the product name. In the first product one table, I'm using primary key based on the product number and category. And I have created another table, which is product 3. It has the same number of columns, but uses product number and product name instead as primary key. So you can see that after inserting a sample record, when I select the data, you can see that in the first case where you have a product number and category are used, so by default, Yugabyte uses the first column as the hash column, and the second column will be the clustering column, which is uh, which is based on ascending or descending. Okay, by default it is descending. Oh, sorry, it is ascending. Sorry. So if you can see the data here, when I run the select star, you see that all the data is ordered by product number. In fact, actually, if you have a multiple nodes, the data will not be ordered by on a product number, but on a product number, it will be ordered by category. So since I have one node, this is showing 1, 2, 3 in a ordered fashion, but in a multi-node setup, it will not be the case. You will find 111 ordered by category, but the 213 can be in other form, other sequence. Okay, and the same data, if I look in the product 3 table in the below, you can see that now the data is ordered by the product name, which we have changed in the primary key. Okay. So the main purpose of demonstrating this or showing this example is in a simple few regards, we will not be able to understand the significance of this ordering, but I'll show you a quick example of how this key or key selection affects the query performance. Now, this one, I have a Docker cluster running. So the Yugabyte is running in a Docker in my local desktop. So I will be using that to connect and create a couple of tables and then show the difference. So once I'm in Docker, I'm connecting to the Yugabyte. So once I am in Yugabyte, so as you can see here, I'm doing two table creations and inserting some data. The two tables have different primary keys. So after the data is inserted, I will run the same query on both of the tables, and you can see the time difference or the effect of the selection of the primary key selection on the queries. Inserting the will just take a few seconds. So after the data is inserted, I'm going to run the query on the product 4. Okay. So for product 4, as you can see, the primary key is based on the product number and prod name. Okay. But in my where condition, I have a product number and I am selecting based on the category. Okay. So here you can see that the execution time it is taking is 5 milliseconds. So what it is doing is, so in this example, as you can see in the mod and an example here, right? So I have 1,000 product numbers repeating, and then the values here, right? So, uh, so for every product number, we have 1,000 records. Okay, so let's run the same query on the product 5 table, which has product number and category as the primary key. So as you can see, the execution time for this is 1 point some milliseconds. And primarily, I want to highlight you that if you see that explain plan for the product file, it uses both product number and the category for index condition. And in the product 4 table, it uses only the product number for index condition. And once the index condition is satisfied, it has to go through all that records which has the product number and filter for the category. So to just show you, I mean, I can run this query again to make sure that we are getting the same numbers or this observing this behavior multiple times. So you can see that product 4 is around 4 milliseconds, but product 5 is 1 millisecond around. The 3 millisecond extra in this case is actually used to go through all the 1,000 records to get that particular category in the product 4 table case. Okay. We just show you one the one observation actually. So since in this particular example case, actually, I'm using same pattern for the data, right? So if I can see the data inside product 4 sample records, you see that 976 is ordered by product name, right? I mean, like we discussed earlier, I mean, simple example, because that is the cluster key. In the product 5 case, so both are showing similar data, because incidentally for these examples, I'm using the same same concatenation value. So that is why both are similar condition. But even though the data is stored in the same format for both the tables, product 4 and product 5, you can observe that by having the right primary key, the execution time varies significantly. Okay. Hope this gives you some idea about how the data is stored in Yugabyte. And when you are designing, you will be able to consider the storage model so that you can design your application and the queries effectively. That is all I have in the demo. And this one I'm flashing again to show you that this quick example will give you a quick visualization of how the storage is actually happening in the DocDB level. So that when you're running a query or designing a query, you will understand, or you will think about or visualize to optimize to select what is the proper primary keys on that or secondary keys. Hope this session is useful. Thank you for joining the session. You can join us if you have any questions or any doubts. You can follow us in the Slack or GitHub. You can raise issues. Hope you'll have a good day and enjoy the rest of the sessions. Thank you.